Okay, so let's summarize what we did in the previous lecture because we want to follow the same mathematical approach. So we had an equation, a differential operator acting on the electric potential. We want to know what the electric potential is. And the source of this is the charge density. And we ended up with the electric potential being equal to the integral over the charge density. Right? We integrate the charge density, the solution to the point source equation. So when we have a point source here, we have this solution, and the general solution when we have many point sources, if you will, a continuous distribution looks like that, where the source appears in the integral, and so does the solution to the point source equation. So by analogy, we'll end up in the same place. We have a linear operator for our quantum field, right? So we have phi double dot plus, well, let's write this, sorry. Let's write this as an operator, right? Sort of like this. So we have two derivatives in time plus, well, we have in our one-dimensional system, we have two derivatives in x. This could be a del squared plus m squared phi. Now, phi is the free field, the free quantum field. Right? Once we put commutation relations on this, it's a free quantum field if that's equal to 0. So this is our free field. And in the video on the real scalar field, we added a potential V of phi. And this is not a free field. And we ended up with an equation which is not just two derivatives in time. So we have that. We have two derivatives in x of phi plus m squared phi, but we also end up with a minus dv by d phi. Rather, we should put this over here. So we have, well, I should have put it over here. So, but that's the differential operator acting on phi, and then that's equal to something here in the same vein as this equation. This is what we would call the source, in the same way that we call the source of the electric potential the charge density. So let's think about, so this represents a, right, it's a kind of force, if you will. It's an interaction term. And so what's the solution, phi, to this equation? And so we want to consider, by analogy, two derivatives in time plus two derivatives in space plus m squared phi. And this, we want this to be proportional or equal to some function here where it's a delta function. Right? So get rid of this. This is some source term. Let's just rewrite this equation such that it's on the right-hand side. So it looks like, right, mathematically it looks like this one. So this sort of represents a field that's almost free. Right, except there's a kind of disturbance at a specific location represented by the delta function. So let's say phi 1 is the solution to this, right? So the solution to this, well, let's put phi 1 there, an analogy with what we did over here. And therefore, we know that our general solution will be phi equals phi 1 our source is this, right? Here it is. And we're integrating, well, we need some subtlety here, but this is special relativity, so it's all the coordinates, right? This really can be written as d mu by d mu. This has to be relativistically invariant. So it's space and time, and that has to be reflected in our solution.